Welcome, everybody, to our Fraunhofer IPMS webinar. I will moderate today's session a little. I am Nora Haufe, the Group Manager of Nanoanalytics Group called Advanced Surface Characterization. We focus on semiconductor materials and techniques. The speaker is my colleague, Dr. Jennifer Amara. She's working in the same team. And today's topic of interest, it's about X-ray photoelectron spectroscopy in detail with our tool, the Phi Quantus Scanning XPS HAXPES Microprobe. And before we start, just some organizational information. For all your questions that arise during the talk or in general, please use the chat function of your webinar toolbar. And we will address them at the end after the talk, and I will read them out and Jenny will try to answer, of course. The whole talk and Q&A will be recorded and available afterwards as well. So yeah, that's everything from my side. Jenny, we all are looking forward to your talk, and the stage is yours.
Thanks a lot, Nora, for the kind introduction. And let's go ahead and start. So as Nora said, we work in the Advanced Surface Characterization group. And today I'll be talking to you about the XPS technique, some basic theory, introducing the new Phi Quantus Scanning XPS HAXPES microprobe, and some of our applications. So to start off with, just a little bit about us. We are Fraunhofer. We are the world's leading applied research organization. We have 75 institutes throughout Germany and about 30,000 qualified scientists and engineers. About Fraunhofer IPMS CNT, and IPMS stands for Institute for Photonic Microsystems, and CNT is Center Nanoelectronic Technologies. And we are located in the city of Dresden in Germany. We are situated close to semiconductor silicon wafer technology companies such as Bosch, Infineon, GlobalFoundries, and X-FAB, and of course, other Fraunhofer institutes. And we do research with companies and institutes for 300 millimeter wafer applications. At Fraunhofer IPMS CNT, we have a clean room where we handle 300 millimeter wafers from preparation to material development to device characterization and application. And here are some examples of our research topics, such as back-end of line integration, non-volatile memory, low power applications, neuromorphic and radio frequency characterization, quantum computing, and spectronics. And our 300 millimeter services include electrical characterization and our group advanced surface characterization. Our advanced surface characterization group focuses on nanoanalytics. And for our cleanroom throughput, our group is concerned with analytics where we work on smaller samples from those 300 millimeter wafers called dyes. We are well equipped with lab facilities and inline metrology. We are a 9-member team and we offer a variety of analytical characterization methods in our labs for chemical, surface, imaging, phase and crystallography, and so on. And we focus on nanomaterials, devices, 300 millimeter wafers, and thin films. And on the right here, you see examples of the many characterization tools that we work with, such as optical microscopy, atomic force microscopy, AFM, which helps us understand, for example, thickness and roughness profiling, SEM, which is scanning electron microscopy for imaging, focused ion beam for sample preparation, slicing of samples, and as well imaging, transmission electron microscopy for imaging, which is also coupled with phase characterization, X-ray photoelectron spectroscopy, which is the topic of today, which helps us understand the composition and phase characterization. TKD is transmission Kikuchi diffraction, which is a relatively new technique, and it helps with texture analysis. TOF SIMS is helps with elemental composition, so it's time of flight secondary ion mass spectrometry, X-ray diffraction for crystallography, wafer mapping, for example, on your 300 millimeter wafer to understand thickness uniformity, and Raman spectroscopy to understand the chemical composition, structural fingerprint of your samples. We do have detailed scientific expertise in both X-ray photoelectron spectroscopy and transmission Kikuchi diffraction. Now, let's go into the topic of XPS. So what is photoelectron spectroscopy? What is XPS? So XPS is based on the photoelectric effect. With this effect, we have photon excitation from a sample surface. Then normally the photon energy should be greater than the binding energy of an electron, and you have emission of electrons into vacuum. What is XPS? XPS is X-ray photoelectron spectroscopy. It's a surface-sensitive technique that probes the occupied density of states of solid surfaces and thin films. Our electrons here are excited by this photoelectric effect, and the energies of the photoelectrons ejected are analyzed by an analyzer. And from this, we obtain information on the chemical state and the mental composition of a sample. Here we have a basic energetic level diagram. We have our filled core energy levels at the bottom. We have our valence band, our conduction band, and so on. And in XPS, X-ray source comes in, excites the electrons from the core levels, and they are ejected as photoelectrons. These photoelectrons are then have a detectable kinetic energy. And using the kinetic energy that's measured and the X-ray energy value, the binding energy of the respective electron can be determined. Here, I just want to show examples of the limitations of the analysis depth for the types of methods that I already mentioned. For example, atomic force microscopy, TOF SIMS, XPS HAXPES, SEM, Raman, XRR, TEM, and XRD. And here, the spot sizes of these techniques are not to scale. It's just to show you the different analysis depths. And it is evident here that XPS is a surface sensitive technique in comparison to some of these techniques. In our work at the Institute, we do deal with thin layers on average of 10 nanometers, and this is exactly the type of method that we need for our application. So let's continue now with the basics of XPS. On the right-hand side, we have a simplified energy level diagram like we saw earlier, and on the left-hand side, a sketch of a material, let's say, deposited on a substrate. And XPS is commonly performed under ultra-high vacuum. So we have excitation of our sample, for example, using an Aluminium Kα X-ray source with about 1500 electron volt in energy. We probe our core energy levels. We have photoelectrons emitted with our kinetic energy. Like I said before, the binding energy can be back calculated. Now, the core energy levels have a characteristic density of states. And as the photoelectrons are ejected, the spectrum is recorded mirroring these density of states. So up here you have a survey spectrum, which gives an overview of all the elements in your material. This is, for example, a survey scan of a doped hafnium oxide material. Here we have a high resolution scan of hafnium core orbital level 4F. So we can tell, like I said, from the survey spectrum which elements are present. When we fit our peaks, we can get the position, which gives us an idea of the oxidation state. When we fit the areas under the peaks, we have an idea of our elemental concentration, and therefore we determine our composition. Now I will switch to speaking about our instrument. So our instrument is the Phi Quantus from Physical Electronics. It was installed in June 2019, and it's an innovative and exclusive instrument. It has a unique lab-based combination of a multitude of features, which I will be explaining to you. The capabilities of our instrument are many. Some features that we have is that we have dual monochromatic excitation, meaning that we have both aluminum and chromium Kα X-rays. Aluminum X-ray is around 1486 eV, and the chromium X-ray energy is about 5400 eV. We have a shutter that automatically switches between the sources during measurement, which makes measurement quite fast. We also have the possibility to do microarray analysis, where we can adjust the excitation source beam size and therefore multi-point analysis. We can do point, line, and area analysis. We also can do X-ray imaging, sputter and angle profiling, and we can use Chromium Kα for depth profiling without the need for sputtering. And we can also do in-situ temperature measurements ranging from -120 to +300 degrees Celsius. The types of samples that we can measure are conductive and non-conductive, wafers, foils, and powders. We can introduce samples through air or inert atmosphere. Ideally, size is about 1 by 1 centimeter squared, but you can also go up to, let's say, 7. But the smaller the sample size, the better, which means you have higher throughput. Samples can be mounted down using a number of ways. For example, double-sided non-conductive tape, as you see here on the left side, or you can also screw them down using a mask and screw on the right side. We have multiple sample holders for different measurement needs. So you have a standard platen, which is just a flat surface where you can mount your samples either by using tape or mask and screw, and you can normally measure with a takeoff angle of 45 degrees. We also can, since we can do temperature measurements, we also have a special holder for this. We can also do electronic measurements. And we have a special platen for angular measurements, which we can go from 5 to 90 degrees and as many steps as you require. So why do we want dual X-ray sources? Here, there is a simple diagram combining a scale of a wide range of elements ranging from lithium to uranium. On the left-hand side, you see core energy levels from shallow to deep states. There is a color coding where the sources can excite, and it's clear that chromium can reach heavier elements and higher binding energy core lines. Both sources, therefore, measure to different energy ranges. On the right-hand side here, you see an example of a survey spectrum for 10 nanometer doped hafnium oxide thin film. On the x-axis is the binding energy, on the y-axis is our intensity. And the black curve here corresponds to a survey spectrum taken with aluminum Kα, and the purple with chromium Kα. Sorry. Aluminum and chromium Kα are complementary excitation sources since they both help to resolve peak overlap, access higher binding energies, reduce surface contamination effects, especially if you use chromium Kα, and sputter damage. So next I will be talking to you about imaging. So we have something called SXI, which is X-ray induced secondary electron images, and this is really helpful in the analysis of structured samples. We can do real-time imaging using the X-ray source that we also use for measurement. We can image structured and inhomogeneous samples. You get SEM-like images for point and line and area analyses. And since we use the same optics for SXI and XPS analysis, this really guarantees that the data is collected from the chosen point and area of interest. So at the bottom here, we have, for example, on the left, a capacitor structure with a defined measurement point as the red cursor that you see. And on the right-hand side, you see a sample which has inhomogeneous surface. So at the top, you see a sputter analysis area from top SIMS. And at the bottom, you see a contamination area. So this can help you find your way around unwanted features. Since we can tune our X-ray beam size, we can do microarea analysis. For aluminum Kα, we can tune it between 7.5 and 200 micrometers, and for chromium, between 14 and 200 micrometers. This can help us with efficient setup and analysis of multiple measurement points across different samples and multiple holders. And it can also, in addition to SXI, create precise measurement spots. There are several ways to do analysis depth with our instruments in order to look at single or multi-layer stacks. This allows the measurement of different thicknesses, it allows the measurement of buried interfaces, and it gives you information on elemental diffusion and composition throughout the bulk of your sample. One way we can do this is using argon ion sputtering. So you see a nice sketch here where you have a sample film on the substrate and you simply use argon ion to bombard your sample surface. In the plot here, you see a plot of sputter time on the x-axis versus concentration of your elements on the y-axis. For example, you have 3 different layers here with different composition. The first layer with ruthenium, the second layer with cobalt, and the third layer with tantalum. And using argon ion sputtering, you can obtain a depth profile. We can also tune our ion gun voltages, and this is important because this helps us control the rate of sputter and damage. Another way we can do analysis depth is with dual excitation. So, for example, normally aluminum Kα can measure up to 10 nanometers in depth, depending on the material and its density. And chromium Kα normally can measure up to 3 times deeper in probing depth. For example, you have a plot here where you see, again, binding energy on your x-axis, intensity on your y-axis, and it's comparing a silicon to S signal at an angle of 60 degrees. And you can see with the aluminum Kα that you still do not reach the silicon substrate, you do not see a signal. However, with chromium Kα, you can clearly see a signal at this given setup. So this tells us that with chromium, we can indeed reach deeper probing depth. What's also interesting about this is that we can therefore do depth profiling without the need of sputtering. And for any materials that are sensitive or degrade, this can help us avoid ion-based damage. We can also do angle-dependent measurements. This can be used for both aluminum and chromium Kα sources. So here, for example, you have a sketch where you see your electron energy analyzer and your sample and the photoelectrons entering. You see, okay, if I am at 90 degrees, I have a larger probing depth than if I am at 30 degrees. So you can tune how far or how deep through your sample you can measure. So I want to show you today some examples of publications. So we have already published last year a paper entitled Spectroscopic Analysis of Ultra-Thin Titanium Nitride as a Diffusion Barrier for Lithium-Ion Batteries using TOF-SIMS, XPS, and EELS. And what we did in this paper is that we deposited titanium nitride using 2 different deposition techniques, CVD and ALD. And we looked at the effects on this material before and after electrochemical cycling. In this paper, we focused on using aluminum Kα X-ray. We also did angle resolved profiling and argon ion sputter depth profiling. And if you're interested in reading the paper, the link is given. Another publication that we have, which was at the beginning of this year, was to characterize and determine the doping level and composition of phosphorus-doped silicon germanium thin films, which are to be used in CMOS-compatible thermoelectric applications. And here, in this case, we used aluminum Kα. And again, the information about the paper is there. We have a paper that we just submitted last week where we investigated atomic layer deposited lithium titanium oxide, commonly known as LTO, and this is normally used in solid state batteries as an anode. And what we looked at here is that we did ALD deposition. We also looked at how the composition changed depending on the different deposition parameters that we used. And here we're really focused on argon ion sputtering and aluminum Kα as well. There is also a publication that is in the pipeline right now, where we prepared doped hafnium oxide using ALD on high aspect ratio structures using XPS and TOF SIMS. So we characterize them using these two techniques and we are comparing them. And this paper is based on a previous detailed TOF SIMS study that was published by us about 2 years ago. And I will actually be presenting the results for this paper in the EMRS conference end of May, and also in ICASIA, which is taking place in Ireland. So I hope to see some of you there. Therefore, in conclusion, what we can do with our XPS technique, we can characterize composition. We can use our dual X-ray sources. We can do imaging. We can do micro area analysis. And we can look at information depth using sputtering, using our dual monochromatic sources, and using angle-dependent measurements. Here I have some my contact information if you would like to ask questions or give a shout out, or if you want to contact us. And here I have my telephone and email, and if you scan the QR code, you can also get direct access to our Advanced Surface Characterization Group webpage. So thank you for your attention. And yeah.
Thank you, Jenny. Very interesting. I'm just checking. We already have some questions and I will read them one after another. Let's start. So the first question, is it possible to force or remove an electron from the core level?
I don't fully understand the question, sorry.
And from the same person, Mr. Kadir, could you kindly describe the slide number 9 again? Maybe it's connected with this comment.
Here, this is slide 9.
Yeah, can you describe this a little again, maybe? And the question, the first question was if it's possible to force an electron to get removed from the core levels.
So it depends on the energy of our incoming beam. For a given X-ray beam, when you excite your sample, you eject core energy electrons, and therefore this electron is emitted with a given kinetic energy as it exits your sample into vacuum, and this electron energy is caught by your analyzer, and therefore you can back calculate the binding energy of your electron.
Thank you. Another more organizational question. Will the presentation be shared for later reference? Yes, I think we need maybe 1 hour, or latest tomorrow you get an email with the presentation, and also on the homepage you find the recorded presentation later on. And another question for you, Jenny, from Finland. What is the XPS spot size, and can it be used as a line scan or line scanner? Yeah.
Yes. So for aluminum Kα X-ray sources, we can go down to 7.5 micrometers, and we can go all the way up to 200 micrometers. So it's really helpful when you look at structured samples. And we can definitely do point analysis, and we can also do line analysis. So you can measure multiple points across one line, and you can also do area analysis, so close to mapping, let's say. So these are the possibilities.
Thank you. I also have a small question. This second source you mentioned, the chromium, it seems to be very helpful and gives the chance for even more insight. But what's from your experience and knowledge the limits of the usage of this? Is there maybe a damage, or yeah, what do you think?
So it really depends on the type of material you're looking at or you're analyzing. For example, commonly organic-based materials are more affected by X-ray damage. However, this is something that you can determine. So you can do, let's say, a stability measurement over some hours or overnight, for example, over a period of time, pretty much. And you can always choose your elements of interest and just measure over time and see if there are really any changes to the peak shape or the peak position. And this really indicates to you whether your material has an issue with your X-ray. This is normally something that's good to do.
Another question just came in here. Does your system allow XPS on 300 millimeter wafers?
Sadly not. It's a lab-based instrument, so we must break our wafers.
Okay, so if there's more questions, it's now the chance to type them in. Otherwise, I'd like to thank Jenny, first of all, again, and also all of you joining the webinar and listening and participation. And all of you will get the link to the recorded talk, as we already said, and the contact details. And thanks to all of you, and have a good day. Bye.
Thanks. Bye.